Unit 5. That's right. That's right. Unit 4, triangles. Unit 5, better triangles. Ladies and gentlemen, better. These triangles are better. The premise of Unit 5 for the test, we're going to use symmetries that we know about certain kinds of triangles to reduce the necessary elements in order to solve the rest of the triangle, with the ultimate goal of reaching trigonometry, in which case, using trigonometry, you can solve everything in an entire triangle knowing as little as possible. Very nice. So, I'm going to begin here with the proof of the Pythagorean theorem. I don't know if I'm going to do all the questions. I don't know if I have time for that. It's already like 5:30 p.m. and the other videos haven't been working, so I will probably go by ear. Let's see. So, without further ado, I'm going to begin with the proof here. To show that the Pythagorean theorem is true here, and especially I'm going to read this question as is. This will be on the test, so star it if you're in honors. Okay, if you're watching this and you're in on level, this is not going to be on the test, so let's skip this. Ready? When the class was asked to form a square using 4 congruent right triangles, just like we did in class, Jose and Iris made 2 different shapes. Use one of their shapes to derive the Pythagorean theorem. It says Jose and Iris, but this says Janelle, so I'm guessing this is supposed to be Iris. Okay? Use one of their shapes to derive the Pythagorean theorem. Show all steps neatly. Will you use Jose or Janelle's shape? Okay? In class, I showed you guys this shape. Both of them work. Notice that they're the same. Like, see that this square is the same size as this square. And notice that each of these triangles is the same. They both have A, B, and C. This triangle also has A, B, and C. Alrighty? The only difference is if you use the Pythagorean theorem in this case, if you try to solve and find out, in this one, you end up writing the expression a little bit differently than we did in class. No big deal, though. So, remember that our goal here is the Pythagorean theorem. Okay? Whenever you're doing a proof, even a proof like this, we're just going to ask ourselves, what do we see about this shape? Write something we know to be true, and get the Pythagorean theorem as a result. So, I'm just looking at the shape and writing something I know to be true. Ready? I see that the area of this big square here is comprised of 2 things. There's the big square. This area is composed of the little square plus 4 times the area of all these triangles, because there's 4 triangles. So, to write an expression for the area of the Pythagorean theorem, all right, I'll just do it in this fashion. If this length is A and this length is B, all right, and it's giving us capital letters here. I don't care for that. Capital letters are typically reserved for points in geometry, so I'm going to be using lowercase letters. Ready? Here we have A and B. So, and also this square has a side length A and B. So does this side. So one length of this square together is A plus B. And then to find the area of that square, we just square it. So the big area here is given by A plus B times itself, which hopefully you agree with. The area of the little square, you can see that this length from the inside is C. So length times width for this square, this area is C squared. Okay? And then here we have the 4 triangles, and each triangle has an area of half the base times the height. So here we see that A and B are perpendicular to each other, so A and B are the heights. We'll do A times B for this situation, and hopefully you can sniff the Pythagorean theorem from one of these. You guys don't have to do both. I'm going to show both just to show it. Okay? Maybe that's the flex here by this question. I'm going to do it both ways because I'm better. I'm better. Anyway, so we can A square. When I guess what I'm really doing here is I'm foiling, right? So should I show this? Surely we know how to foil. Maybe I show it anyways. Let's see. So on some scratch paper, A plus B squared. This is the same as, if you don't know what to do, ask yourself, what does it say? This is the same as A plus B times A plus B. A times A is A squared plus, and then on here we have an A on the outside, we have A times B. On the inside, we have B times A. That's 2AB plus B squared. Lovely, beautiful, wonderful, gorgeous, incredible. Okay, so this is what we're going to plug in on this side. Your algebra teacher may have just made you memorize that, if you're fortunate. Okay, and then here we have a c squared, and then 4 times a half is 2, so this is a 2ab. And then look at this. This proof is screaming to be solved. Look at this. We have here 2ab's on both sides, so they cancel, and the final step is a squared plus b squared is equal to c squared. So just to show that it's a proof, we'll write therefore this happens, and then I'm going to do my little signature there at the end. QED, we've shown the Pythagorean theorem to hold. Okay. Now, why does this apply the Pythagorean theorem? Because A, B, and C are on a right triangle. You could take any right triangle you have, duplicate it 3 times, and create this square shape, and this property would always hold. The same is true for Janelle or Iris's shape, except it's a little bit different. I'm going to do the same thing. We have an area of a big square. Alrighty. And that's going to be equal to, area of this big square here is actually C, in this case. And then on the inside, we have A and B together, C and A and B all intersecting and doing crazy stuff. So what I'm going to say here, I just looking at the shapes, we have a little square on the inside as well, and then we also have the additional 4 times the area of the triangles. Alrighty? Very cool. Now look, very similar first step here. There's a big square, there's a little square, there's some triangles. Okay? So this is why the proof is fascinating. It doesn't matter if you were Jose or Janelle, you can arrive at the same conclusion. Why mathematics is cool, right? You can arrive at the same conclusion regardless. Anyways, so to make sure that we're being consistent here, notice that the area of the big square is C times C. So this area is going to be C squared, C times C. The area of the little square is a bit odd. Notice that this length is an odd length. So this whole length is A, but then you have to take away B to be able to find this length. So this length on the inside of the square is A minus B. Interesting. A minus B, which means this area of the small square is given by A minus B all squared, plus 4 times the area of a triangle. And same as last, these are the same exact triangles, so they'll have the same area. Base times height, 1/2 base times height. And look at this. Hopefully the astute among you see something very similar happening here. All right? There's a slight difference, though, in how this is approached. Here, A minus B squared. Sounds like there's someone speaking outside my window. Listen. There's people outside. Oh my gosh. Anyways, hopefully they don't hear me basically yelling at no one in an empty room. Look at this. It's so depressing. Got the lights off, though. Pretty sweet. Anyways. This is what they say, guys, to engage your students. You have to change it up, you know? You got to just show everybody the room. Okay? Anyways, we'll follow this out. First, outside, inside, last. A minus B times A minus B. So this one's a little bit different. It's a lot like the other one we just did, but it's a little bit different. In this case, A times A is A squared. That's the first. Then we do outside and inside. That's A times minus B, and then minus B times A. So that's minus 2 ABs. There's 2 negative ABs in this case. So the difference is, earlier we had a positive AB. And then here, negative B times negative B is positive B squared. Excellent. So that's what we'll substitute in for this side. So here on this, I get C squared equals A squared minus 2AB plus B squared plus 4 times 1/2, which is, of course, 2AB. And now look at this. I have a plus 2AB and a minus 2AB. Interesting. And, of course, they cancel. And we're left with C squared is equal to A squared plus B squared. So you can kind of see in the result, these proofs are saying the same thing, but in a slightly different way. Fascinating, okay? If this is how your brain sees the picture, then you result with C squared equals A squared plus B squared. If this is how your brain sees the picture, then this is the result. Of course, we know that these results are no different because of the symmetry of equality, which is very nice. That's the proof summed up. I'll see you in the next one.